Thank you, Andreas. Is this switched on? Can you hear me in the back? Yeah, all right. Three prisoners were sentenced to death. One of them French, one of them German, one of them American. What is your last wish? They ask the French guy. He says, a bottle of exquisite French wine. What is your last wish? They ask the German guy. He says, I want to give a speech. What is your last wish? They ask the American guy. He says, I want to get shot before the German starts his speech. Unfortunately for you guys, it is too late now. My speech will be about the deep learning renaissance. This is my name. This is how to pronounce my name. And deep learning is a new name for an old hat. Deep learning is about credit assignment in neural networks with many computational stages. And that goes back at least 50 years. Recently, we could see popular science articles without peer review, which seemed to leave the impression that this was invented recently. But no, it really goes back a long way. And just to make this clear, I wrote this survey, which you can easily find, Deep Learning Overview, if you type that into Google, or if you follow the link down there, where there's a history of the field with over 800 references, if you're interested in that. And by the way, many of my slides have a little web page associated with them, and you click there and you see more details and details in papers than you wish. The first deep learning pioneer was Ivaknenko, 1965. And what he did in 1965 already was neural networks. He didn't call them neural networks, but that's what they were, with many layers, where first you had input units, and then there is a first layer of neurons, and each of these neurons could do was connected to some of these input data, and it could compute a Kolmogorov-Gabor polynomial of these input units, of the real-valued activations that it found down there. So having multiplications and additions in there, and then could adjust its weights using regression analysis, which back then was about 200 years old. Gauss and Legendre. And then he took the activations of this output layer, of the first layer. If he wasn't able to train that to do some classification or prediction in the desired way, then he added another layer on top of the first one. And the next layer got the connections from the layer below, and so on until he got satisfactory performance. And he also had a way of pruning units in the networks that didn't do useful things. And for that purpose, he had a separate validation set. He didn't use the word validation set, but that's what it was in today's terminology. And he used it to see which of these feature detectors in these layers didn't really contribute anything to the improved performance, and so he removed these then. So he had growing and shrinking deep networks. In 1971 already he published a paper that described an 8-layer network. So deep learning goes back 50 years easy. What he didn't do, he didn't train these networks by backpropagation. Does anybody know what is backpropagation? All right. Does anybody know what is a neural network in general? Okay. Does anybody not know what is a neural network? An artificial neural network? Is there a third group? All right. And is there a fourth group that is already asleep? Okay. So backpropagation is this method for computing a gradient with respect to some error at the output layer of a neural network like this, such that the error, which is the difference between what the network does and what it should do, at least in the supervised learning case, such that this error can be minimized by computing a gradient with respect gradient of this error with respect to every single parameter in the system, to every single weight on these connections. And this also goes back to the same decade when Ivagnenko did his thing, to the 60s. And often you find misleading accounts of the history of backpropagation, but in this recent survey I tried my best to really track down who invented this. So this goes back to the beginnings of the 60s. In 1961, Bryson and Kelly, they had the basic calculations already done, deriving backpropagation in the context of the calculus of variations, using dynamic programming to compute how should you propagate errors from the output layer down to the next layer in a recursive fashion that is efficient, in the sense that you need just as many operations for the gradient calculation as you need for the forward propagation phase. They didn't use neural networks, but they adjusted control parameters of systems, and this was essentially a continuous version of backpropagation. Dreyfus, from this place, from the Bay Area, and I think even back then at Berkeley already, he in 1962 had a simplified derivation of the same thing using the chain rule only and no dynamic programming. Now, the guy who described the modern version of backpropagation in discrete, sparse networks with shortcut connections, that was Linnainmaa, Seppo Linnainmaa here. That was a Finnish master student, and that was his master thesis. And there you can find backpropagation code also. In his thesis of 1970, he was not interested in neural networks, though. He derived that just for general systems where you have to where you have to compute derivatives of errors of these type. And the first guy who apparently used this technique to adjust control parameters was in 1973 Dreyfus again. The first guy who applied this to neural networks, that was apparently in 1981 Paul Werbus. Not in 1974 in his thesis, but in 1981 in a little paper that he had there. And later then, in the 80s, many people applied that to neural networks, and Rumelhart and colleagues had experiments that showed how backpropagation can learn interesting internal and useful internal representations for all kinds of problems. And then there were extensions for recurrent neural networks where you translate recurrent networks with feedback connections, where there's an input stream coming in, where you translate these networks into huge feed-forward networks, very deep feed-forward networks, such that you can get the gradient calculation right. And here I'm always citing Werbus and Williams, Ron Williams, and Robinson and Forsythe. So these recurrent networks, they are the most general and deepest of all networks. They have potentially unlimited depth. And here we see a recurrent network that has 2 input units and 4 other units, and 2 of the other units are output units also, and all units are connected to all non-input units, so that is a fully recurrent network. And in reality, these networks are much bigger, because if you want to, for example, observe videos, then you need many more inputs than just 2, and each of these units, the input units at a given time, adopts a certain value corresponding to the pixel that it just sees there in the video stream, and in every second 20 new frames are moving into the system, while the old inputs still are circling around within the network because there are these recurrent connections. And each unit at every given point in time just sums up the weighted activations of those guys it is connected to at the previous time step. And this is a general computer. And the program that is running on this general computer is the weight matrix. And searching for programs on these recurrent neural networks is a very general and universal thing to do. So the search space is really general. And for example, what we can now hopefully do is find a program, a weight matrix, that takes video that comes in and translates it into output actions, for example, to drive a car. And I'll tell you later an example, I'll show you an example where this is actually the case, where a network learns from scratch, from nothing, to drive a car based on video input. Only a simulated car in a video game, I have to say. But nevertheless, with full vision. At the end of the 1980s, it turned out that deep learning doesn't work. At least not in the supervised case as often used back then. And the reason why deep learning in networks with many computational stages, or in recurrent networks where you essentially have a new layer for every single time step that you are observing, or for every single time step of a sequence that you are processing. The reason why this doesn't work was analyzed in 1991 for the first time by my former student, Sepp Hochreiter, who is now a professor in Linz. That's a more recent picture of him. And he was a master student back then, and he showed, in my first deep learning project, 1991, he showed that as you are trying to propagate errors back in these deep systems, they become smaller and smaller. They become smaller and smaller, and they actually vanish exponentially in the number of layers that you propagate them back. That is, after a few layers, maybe 10 layers, very little is left, and you can't really learn anything that has many computational stages, or you can't really learn much about sequences where you have to memorize events for long time lags. Again, for all of these slides, there is a little link, and it's also easy to find on Google, where you can find more details and original papers. And then my first deep learning system, which tried to overcome this problem, was a stack of recurrent networks, also 1991, published in Neural Computation, 1992, where you try to do not only the sequence processing not only with one recurrent network, but with a stack of networks. And the idea is that each network learns to encode the incoming sequence in a more compact way. Remove some of the redundancies, discover some of the regularities, feeds then this compressed description to the next level, which maybe finds an even more compact representation, and so on, until finally the highest level has such a compact representation of the sequence, the observations, such that supervised learning, given this compressed representation, is much easier. And the basic idea is unsupervised pre-training. So you first have a recurrent network on the lowest level, which just tries to predict the next input given the previous ones. And you can train it using backpropagation through time. Just compress your time series by predicting the next thing given the observation so far. You train that for a while, and then whenever you correctly predict some input, then the information in the input is not new because it was already within the weight matrix of the network because it was able to predict it. So you don't have to store that extra. Only the errors, the unpredictable pieces of information, only they convey new information, and that means that I can encode the sequence by the errors that the lower level makes. Because given these errors, I can reconstruct the sequence using the information contained in the weights of the lower networks. So whenever there's an unpredicted input, I feed it to the next level, and it ticks on a much slower time scale, assuming that the lower level has lots of temporal irregularities that allow me to predict away many of these inputs. And then maybe there's a second level of predictability on the higher level, and again get maybe an even more slowly ticking network on a higher level, which ticks only when there is new information coming up from below. And using this simple system, then, we were easily able to solve deep learning tasks where credit assignment had to pass 1,000 steps back into time, which were not solvable before. And very similar ideas came up later then in the new millennium. Does anybody know is a deep belief network? Deep belief network. So there you also have a stack of networks, but they are less general than these recurrent networks. They are feed-forward networks, and each of them tries to more compactly describe the input. In fact, each of them tries to maximize the log of the probability, in other words, minimize the description length of the data. That's exactly what the old system of 1991 is doing. And so once you have an unsupervised pre-training based system of this type, you can then fine-tune it using standard supervised learning to achieve some classification result, to do pattern recognition, sequence recognition, and so on. Did you understand what I just said? Does it make sense? All right, okay, yeah. So, you know, before I came here, I thought this is going to be just a little tech talk and there won't be much of an audience, but you are actually a large audience by my standards. The other day I gave a talk and there was just a single person in the audience. A young lady. I said, young lady, it's very embarrassing, but apparently today I'm going to give this talk just to you. And she said, okay, but please hurry, I gotta clean up here. So in the beginning of the 90s we had these unsupervised pre-training systems, but now but then in the course of the 90s we completely replaced those by purely supervised, purely discriminative systems called long short-term memory recurrent neural networks. Has anybody heard about these LSTM recurrent networks? So some of you, but many of you don't know what that is. This is now state-of-the-art in connected handwriting recognition, in many aspects of speech recognition, and is probably good enough to do speech recognition from end to end, where you have raw speech coming in and you represent recognized words and sentences just as letter sequences. So the basic idea of these recurrent networks is very simple. They overcome the fundamental deep learning problem identified in 1991 by Sepp Hochreiter through a stupid, simple trick embodied by this red unit here. Do we have maybe a laser pointer? Laser pointer? Or a stick?
Behind you.
Oh, there. Thank you. This is a linear unit with an activation function which is the identity activation function. X translated to X, which means that whatever is in this unit here doesn't change from one step to the next, assuming that this weight here, this connection from the unit to itself, has a value of 1.0. So for now we assume that the value from here to there, the connection weight is 1.0, which means that as I'm propagating backwards through a unit like this, I always have to multiply with the activation of the activation function, but with the derivative, first derivative of the activation function, which is 1.0. So nothing changes. The error flows back in time not only for 10 or 100 or 1,000 steps, no, for millions of steps. until it flows out of the unit. Of course, with linear units like that, we cannot do much sequence classification. So that's why we surround this red unit by a whole cloud of multiplicative or otherwise nonlinear units, standard nonlinear units. And they profit from the error signals that are propagated backwards through these guys for thousands of steps until they flow out here. This is a multiplicative unit, for example, and they change all the connection weights in the standard fashion just using gradient descent. So every weight is learned, but the weights to the nonlinear units, they profit a lot from the red units, which are called constant error carousels, where errors can flow back for thousands of steps. And this simple trick allowed us to solve many deep learning tasks without any unsupervised pre-training, which were unsolvable before. But back then in the 90s, we only had these little tiny toy experiments. And today, with much faster computers, lots of stuff that sounded like science fiction back then became possible. In the 90s, speech recognition was really dominated by hidden Markov models, combination of hidden Markov models and neural networks for estimating the transition probabilities and so on, but the core was usually a hidden Markov model. And this is now changing, I think. I'm lucky that the Swiss National Science Foundation and the German National Science Foundation, that they funded this work even during the dark ages, which lasted from 1995 to 2003 roughly, when support vector machines were much more powerful in many applications and in many contests than neural networks. In the new millennium, LSTM networks suddenly became competitive, at least in certain limited aspects of speech recognition. For example, keyword spotting. And here we see a picture of Santi Fernandez, who also used LSTM networks to process speech. And that was in 2007, where there was not only a simple LSTM network, but a whole stack of LSTM networks to to pick out keywords in speech data, and that worked very well there. You know, keyword spotting, that is when you listen to a phone speech and somebody says Al-Qaeda and a red flag goes up. And fortunately, this not only has applications for the fights against terrorism, but also commercial applications such as industrial espionage. And then in 2009, for the first time, recurrent neural networks won competitions. In this case, handwriting recognition. Here we have a sentence, to be willing to hear, and it's handwritten, so the teacher doesn't really know when does this I begin and this N start, and he doesn't know that for any of these details of the real valued sequence that the network processes in sequential fashion. The goal is to translate this long real valued input sequence. Could be a video of the sequence, or maybe you have a device where you get X and Y and pressure coordinates from somebody who is online writing this sequence here. You want to translate that into T-O blank, B-E blank, W-I-L-L-A-I-N-G, and so on to here. And the way to solve that problem is to maximize the probability of the label sequences given the long real-valued input sequences. And there's a way of computing a gradient of that. In particular, if you have chunks of speech data that you can process both forwards and backwards, then what one should do here is to use bidirectional LSTM networks. Does anybody know what is a bidirectional recurrent network? So a few people know what that is. Let me explain quickly what's happening there. You not only have one recurrent network that tries for each of these real-valued inputs, at each time step of this long input sequence to predict the corresponding label at this point in time. You have also another one which is trying to go backwards, and so it comes from here and always tries to predict the previous label. And of course you have then a combined system, and you add the predictions of the backward guy and the forward guy at every single point in time, like for example here, and the sum of these two predictions is the true prediction, and then there is an error coming in at this point in time, and it flows back in this direction and it flows back in this direction, and in this way at every point in the speech signal you have the entire left and right context, which often is really useful. And then a system like this not only won the French handwriting recognition competition in 2009, but also the Farsi handwriting recognition competition and the Arab handwriting recognition competition. Although none of us speaks a word of Farsi or Arab, and our French is also not so good. Very much the same system recently set the record on phoneme recognition on the timid data set. And this also was done by Alex Graves. So Alex Graves was the guy behind all these victories in these competitions. My former PhD student and then postdoc, and now working at DeepMind. At the ICASP he had the best results on timid phoneme recognition, and more recently it seems clear to many who are using LSTM now for speech recognition that you can do the real end-to-end speech recognition thing. You just feed in the raw speech data, and out you get words. So you do word recognition, but because there are so many words, you don't represent the words as points in a vocabulary of 100,000 or 200,000 words. No, you just represent them in distributed fashion by the letters. And the system itself has to learn that certain letter combinations are good and others are not good, and if a new word comes along, then it's a combination often of existing chunks of words, and all of this an LSTM network can learn, and it looks like we can really have very simple recurrent network end-to-end speech recognition rather soon. Let's see whether this really pans out. Some tasks are so simple that you don't need recurrent networks to solve them. Recurrent networks are general computers. Feed-forward networks are not. On a recurrent network I can run any program that I can run on this laptop, given an appropriate weight matrix. For a feed-forward network that is not the case. But some tasks in pattern recognition, like for example this one, are simple in the sense that the data is already segmented, and this is the most famous data set in machine learning, which has been introduced in 1989 by Yann LeCun and his team. That's the MNIST data set. So there you have handwritten digits, but they are already segmented. So the system already, or the teacher at least, knows what this is. So it can, the system is just trained to provide a label for each of these. Does anybody know the MNIST data set? Has anybody ever played around with that and used it? Okay, quite a few people. Many people have used many different machine learning algorithms to improve their performance, but in 2010 we were able to break the MNIST recognition record using a very stupid, very old, very simple system, namely a deep neural network based on backpropagation. A standard feed-forward network with, I don't know, 6, 7 layers or something like this. No unsupervised pre-training. No convolution, nothing like this. Just plain backpropagation on the data set, combined with another idea which also back then dated back 20 years, which is use your patterns to make additional patterns by shifting them, rotating them a little bit. Do all the things that your eyes do all the time anyway with your training examples. So whenever you have a digit, just transform it in the obvious way that reflects what your eyes are doing. With digits, you also can warp them a little bit. With normal objects such as cats and cars and so, you shouldn't do that. There you should just do the standard things, standard movements. And this was then, this simple combination really led to an improvement of the world record back then, which astonished many people. The main reason why that worked was this was implemented on GPU and was about 50 times faster than previous neural network implementations, and that made the difference. So this approach did not solve the fundamental deep learning problem in a fundamental way, but the system was so fast that it was able to propagate these errors a little bit further down within a reasonable time, and that was good enough to get a new best result there. If you have questions, you ask me anytime. Yes?
Since we're taking a trip down memory lane, where do Hopfield nets fit in?
Yeah, Hopfield nets are, at first glance, recurrent nets of 1981, I believe, and they are like icing models known from physics. Hopfield was a physicist himself, I think, and they are recurrent systems which have an input that remains fixed. It's stationary. So there's not a sequence coming in, but there's just an input pattern, and then the recurrent system is wired up such that it's guaranteed to stabilize and come up with a certain internal representation. And this can be used as an associative memory, and back then it was considered a big deal, and many people used it for all kinds of interesting studies. But today nobody's using it in these commercial applications.
So it didn't have any surviving ideas?
Well, not really, not that I know of. So nobody at the moment is using Hopfield-like methods for any commercial applications, at least, although I'm sure there are still people who analyze theoretical properties of such systems.
What about deep Boltzmann machines? Those are somewhat similar, right?
Yeah, the deep Boltzmann machines, they go back to so Smolensky in 1989 had something which is called a restricted Boltzmann machine, which is a very simple system, a one-layer system, which learns, I briefly mentioned it before, which learns or tries to learn a better representation of the data that is observed, and then you take the representation of the data and feed it into the next restricted Boltzmann machine, and then you get a hierarchy of these. This was published in 2006 by Hinton and Salakudinov. Yeah. And then you can fine-tune the whole thing through backpropagation. So this is one of the systems that has unsupervised pre-training, and then you fine-tune through backpropagation to solve supervised learning tasks. So it's very much like the 1991 hierarchy of unsupervised recurrent networks, except that it's not as general because it doesn't deal with sequences, it just deals with stationary patterns. And the argument that the authors put forward is also that at each level of the hierarchy, under certain ideal conditions, you maximize the probability, the subjective probability of the data, or log probability of the data, which is equivalent to minimizing the description length of the data in the recurrent systems of 1991. But all these unsupervised systems have not really survived, because in the 90s this was replaced by the totally discriminative LSTM networks, and the feed-forward networks in the 2000s were replaced by totally discriminative feed-forward networks like the one we just had, and especially by the max pooling convolutional neural networks. So for the feed-forward case, that's what most people today use to classify patterns, to recognize patterns. What's going on here? There is an image, here's a 2, and then you have a convolutional layer. Does anybody know what is a convolutional layer? A Okay, some know, but some don't. So you have a neuron which has a particular receptive field, a weight vector, and it's a little patch of the original image that it can see, and then you shift this original patch across the entire image, and for each of these inputs that it sees there, it produces maybe a different value, and this is then the value of activations in the first convolutional layer, and there's not only one unit with a given weight vector like that, but there are many different units like that. And so you have then a set of filters that give you a first filtering of the input, and these convolutional layers, they feed into max pooling layers, which are also conceptually very simple. So whenever you have, say, 3 by 3 units in the convolutional layer, then you replace them by the one with the maximum activation. And then you have another convolutional layer. So this is for downsampling. And then you have another convolutional layer, and another downsampling, max pooling layer, and another convolution layer, and another downsampling layer, and so on. And at the very top, you have errors, because the system classified the images down there in a way that you didn't like. So there's a difference between what the network says and what it should have said, and you propagate that back using standard backpropagation. No unsupervised pre-training, and this is what is working very nicely today. The pioneer, yes, there's a question.
How do you get the error signal through the convolutional layer?
How do I get them
through this convolution layer? I mean,
like with standard backpropagation, so you have everything is differentiable, and so you just propagate the errors down. And the architecture goes back to Fukushima 1979. Fukushima had the neocognitron, and this was almost the same thing. So convolution, downsampling, he didn't use max pooling, but spatial averaging, but then convolution, downsampling, convolution, downsampling. And this guy, Weng, he was the guy who in 1992 replaced the spatial averaging through max pooling. And Yann LeCun was the one, and his team was the one who in 1989 applied backpropagation to such networks, because Fukushima used unsupervised learning rules, and so did Weng. So the other two guys, the architecture guys, they focused on unsupervised learning rules, while LeCun and his team had supervised learning in mind. Some of you know the H-max of Riesenhuber and Poggio, 1999, very similar to 1992 Cresceptron of Weng, John Weng. But no training at all. Yes, there's a question.
With your basis functions.
Yeah.
So, I mean, is this something that is still being used in some form today?
Yeah, there are always people who are using other things than that. But at the moment, this stuff is good for and widely used in many competitions. Yeah. And so here our contributions are less profound than in the recurrent network case, because here our main contribution was to make it faster on GPUs, and use ensembles of this stuff, and then win all kinds of competitions with that.
is it good for only like stationary signals or like time series signals?
Yeah, this is really good only for stationary data like this. For time series, you need recurrent networks. So I came from the complex case from recurrent networks and dumbed myself down a little bit going to the feed-forward case. But of course, in many applications, you want to combine aspects of feed-forward networks and recurrent networks, and actually that's what we sometimes do. But this here is now really just for feed-forward image recognition, which maybe you speech guys, who is interested here in speech processing? Yeah, so the pure speech guys, they are mostly interested in sequence processing, not so much in this feed-forward stuff. But the feed-forward stuff also works well for many applications. For example, Chinese handwriting recognition. There you have not only 9 or 10 different digits like with MNIST. No, you have 4,000 different symbols. So you have really a network with 4,000 different output units. And in 2011, we were able to win that contest at the ICD International Conference on Document Analysis and Recognition, ICDA. And in 2013, there was another paper where, for the first time, our system, slightly improved, achieved human competitive, almost human, not quite, but almost human performance on the Chinese handwriting. Of course, this is of interest for all the cell phone producers, because the idea is you go to China, you go to a restaurant, you don't understand the menu, you take a picture of the menu, and the characters are recognized and translated into something you understand. Yes, there's a question.
Is this only for applied to one kind of data or to many different styles of data?
To many different styles of data. So at the moment we are still talking about handwriting recognition, but soon I will come to images. And here, for example, the same system that is good for Chinese also is good for symbols of the Western kind. So again, the MNIST. I told you that we were able to break the record with a plain backprop network, but we were again we were able to substantially improve these results than using max pooling convolutional neural network and got down to 0.2%, and that's human competitive performance. That's the first time that anybody achieved human competitive performance on MNIST. And this is interesting because before that result, for almost 10 years, the record of MNIST recognition error hovered around 0.4, and then suddenly it went down to 0.2, a factor of 50% or 100% if you look at it from the other direction. There's another question.
Does anything change between these two tests?
Not really, and in fact it helps a lot if you pre-train on one set and then fine-tune on the other. So when you learn the first 5 layers using, say, Chinese handwriting, and then you freeze them, and on top of them you learn the European handwriting, that is much faster than you learn everything from scratch. Because the features that the system learns from one data set are actually very useful, generally useful for all kinds of vision tasks. And so you just have to learn a little epsilon on top of that to get the classifications right on this new data set. This transfer learning can often be observed. And generally speaking, all one-shot learning is just a reflection of the fact that you, during your decades of experience with visual data, you got so much generally useful knowledge about vision and other data, such that you have to learn just a few extra bits on top of what you already know once a new data set comes along. There's yet another question.
So you mean you didn't change any topology of the network? So the layers and connections are all fixed?
Yeah.
Only to be learned is the parameter. Right?
Yeah. Maybe we changed a few little things, but there's a broad range of parameters that is good for all kinds of vision tasks. Yeah. Okay. I would not dare now to say it's exactly the same, although in some of the transfer tasks we really used exactly the same thing, just to make sure that there is that exactly the same conditions are used for the Chinese and the European data sets. Yeah. But I wouldn't say that the best performance on the Chinese was obtained with exactly the same architecture as the best performance on the European data set. So there's a question.
Numbers are still meaningful, or isn't it just showing off to the
What was that?
And do you think these small numbers are still meaningful?
No. MNIST is over now. We should have more interesting, larger data sets, absolutely. So the Chinese data set is much more interesting. Yeah. Yeah. If you look at the networks after training, it turns out they invent stuff that has been known in computer vision for decades. In the periphery, you see orientation-sensitive Gabor filters, bar detectors, and stuff like this. And you know this also from studies in neurobiology. And the deeper you go into the system, the more opaque these feature detectors become. Generally speaking, it's all about compression. there are billions of pixels out there in the training set, and you want to squeeze the relevant information down into a few million weights. So you have to compress a lot, and then the best way of compressing this is usually allocate a few neurons and synapses to the stuff that frequently reoccurs in the visual scene. So have a couple of grandmother neurons or other neurons that are more distributed that reflect the stuff that is frequently coming up again and again. Now you said, don't we have other data sets than those related to handwriting? Yes, of course we do. For example, traffic sign recognition, that was a couple of years ago, also not far from here in San Jose. The traffic sign competition, which we were able to win, there was an interesting story, because before the main competition started, there was a qualifying round where everybody in the world could submit to the organizers his favorite, or a system trained by his favorite machine learning algorithm, and then the organizers had a separate test set of traffic signs that were not publicly available for the for training the networks, and then there was a couple of weeks of submissions. And until the last day of the competition, we thought we had a comfortable lead, but then our friends and colleagues and competitors from New York University, Pierre Samanet and Lecun, they submitted yet another entry, and this was just a little bit better than ours. And then Jonathan and Dan and Urli had to work late night just to submit yet another entry a few hours before the deadline, just to re-establish the correct order. But what happened there, teams started to overfit on the test set, although they didn't see the test set, but they were probing it through repeated submissions. So that's why the organizers cut it down at some point and said only 10 resubmissions. So you can overfit on test sets even if you don't know them. In the final competition, this was not possible. No overfitting on the test set was possible. There was one trial, and there the results were extremely clear. Our system by far had the best performance, 0.56% error on the test set of the organizers. Second best system, humans, about twice as bad. And the third best by our colleagues from New York University, promptly hired by Facebook. And the fourth best, that was the first non-neural system, which was, I think, a combination of random forests and support vector machines, something like this. In Switzerland, if you don't obey a traffic sign, you go to jail. But across the border there is Italy, where they also have traffic signs on the street, but only for purposes of decoration. Why is traffic sign recognition important for self-driving cars? And 2014 is the 20-year anniversary of self-driving cars in highway traffic. So 20 years ago, in 1994, for the first time, self-driving cars like this one here drove on the Autobahn, on the highway around Paris, multi-lane highway around Paris in traffic. And this was the pioneer who made this possible. Ernst Dickmanns, who already in the 80s had self-driving cars on empty streets, but then in the 90s he moved into traffic, and he did not use GPS. He used vision, like humans. He had these active cameras in the cars, focusing on the salient points, and tracking up to five cars in front of the vehicle, and up to 5 cars in the back. No LiDAR, nothing like that, just vision. And then in 1995, for the first time, he had this legendary trip where he went from Munich to Denmark and back on the highway. up to often over 100 kilometers without any intervention of the safety driver. There had to be a safety driver for legal reasons and for construction areas which were not modeled. Going up to 180 kilometers per hour. That's more than 110 miles per hour. Much faster than today's self-driving cars. Much faster. No GPS. Today's GPS-driven vehicles, they pretty much know where they are and just need a little bit of extra pattern recognition to avoid getting sidetracked. So 20-year anniversary of self-driving cars. However, back then, the pattern recognition, pedestrian recognition, traffic sign recognition was much worse than the performance of kids, for example. And in 1997, it was a big deal when Kasparov lost against a computer in chess. But no computer back then could recognize patterns, even in limited domains like this one here, as well as little kids, or humans in general. So from a computational perspective, pattern recognition is harder than chess. Yeah, yeah.
So you haven't talked at all about hybrid systems in which the neural network is used for feature extraction, and, and then you use a traditional machine learning classifier on the back end. Would you? And when I talk to commercial people at Google and so forth, that's what they're doing. So I understand you're winning a lot of contests, but in terms of the best system, would you contextualize your work with the hybrid system?
Give me 2 more slides.
Okay.
I like this question. Thank you. So, moving on from pattern recognition and classification to segmentation and object detection. That's what we are going to do now, and there I will try to answer your question a little bit. So we can use the same system not only to classify images but also to segment them. Here we have images of brain slices, and these brain projects in Europe and in the United States, one thing they do is now take a brain and slice it into little slices, and then you get a stack of slices and you put them into an electron microscope and you get some picture there, or a stack of pictures, and then from there you try to reconstruct a 3-dimensional model of the human brain. And to do this, you need a horde of students who label all these images and say, this is membrane, this is background, membrane, background, synapse, and so on. And you want to automate this. So there was a competition where the organizers had a training set already labeled by their best students, and then there was a secret test set, and again, the system that we had here just learned for every single pixel, as you shift a little receptive field across the scene with some context and maybe lower resolution context in the periphery, you just learn for every single pixel is that what that is, given the context. Is that background? Is it membrane? And so on. And so this system also clearly won this competition. In pixel or error, it was better than humans. There was another measure in which it was worse than humans, a measure which it was not trained to minimize, but which the organizers considered significant. So there is still something to do. Same for, this was the first time that a deep learning system of the forward kind, of the feed-forward kind, won an image segmentation competition. Although in 2009 our recurrent networks already won these competitions, the handwriting competitions where you have to segment and classify at the same time. So then the same approach, without much variation, can be used to detect objects. So most of computer vision is really not so much about classifying images, but about detecting objects. And what do you do? Well, again, you take a patch of. So what is this here? This is an image. This is an image of. This is a breast scan, breast tissue. And this type of object detection is pretty important because the little guys here, they are mitosis cells. They are pre-cancer stage cells which you want to detect. And normally you need a trained histologist to go through these images and say this is a mitosis cell, this isn't, so object detection in huge multi-million pixel images. And I'm not able to see the difference between a mitosis cell and a harmless cell. So what we do is we train our network to imitate what the trained histologist does. And then we shift our system across the entire image. And whenever it lights up, then we say, okay, here there's a mitosis cell. And this simple approach also won this, for the first time actually, won an object detection contest. And you can imagine that as you are shifting patches or deep networks across these images, you're going from one pixel to the next, and as you're doing this, there are lots of redundant computations that you repeat all the time. You can imagine that as you're moving from left to right, many of these multiplications have to be repeated, and then it becomes a little bit messier in these downsampling layers, in these max pooling layers, so you have to make sure that you arrange everything as you're trying to remove redundant computations. You have to make sure that everything is in order, but it is possible to do this in a way that allows for very fast max pooling CNN scans, which were first published in 2013. Jonathan Mushi was the first author, where you can speed up the scanning process by a factor of 1,000 or over 1,000 over the naive method. So that's worth knowing. And the same approach then, because the topic is so important, again was used in the MICAI 2013 Grand Challenge, where a larger and bigger data set was provided by the organizers. This, of course, is maybe the most important application of these feed-forward deep networks, because there are so many medical problems that you might be able to address with systems like that. $60 trillion per year, that's about the GDP of the world, and 10% of that, $6 trillion, are spent on healthcare, and a substantial fraction of that goes into diagnosis of sicknesses, illnesses, and so it would be, it's like this can contribute to improving healthcare for all kinds of people who at the moment don't have this type of healthcare, because you really need trained experts to do it. There's a question.
What kind of F-score for this one?
What was that?
What kind of F-score would be precision recall for this time?
This one here? So here it is comparable, not quite, but almost as good as the expert who is providing the labels. And we are imitating the expert, of course, which means that we don't know whether the expert is really providing ground truth. So we are also imitating his faults if he has any. However, there was a recent paper, and there Alessandro Giusti was the first author, where there was a comparison between the deep networks and humans, non-experts, trained on the same images that were used to train the artificial networks. And there, humans were slightly worse. So it's in the same ballpark as non-experts trained on these images, although I can't give you the number you really want to know with respect to ground truth. This is a 10-year-old movie which shows the more interesting type of AI we are interested in, namely not only perceive and classify and so on, but also act. And true intelligence is about interaction with the world, so you see what is the state of the world to a certain extent, you acquire more information about the state of the world through your sensors, you make decisions that optimize your future success in the world, given a model of the world that you're building that allows you to predict the consequences of your actions and so on. So the full sensory motor loop, that is the real goal in AI. Do we still have time at all? Should I finish my talk, or are we still good? Who knows that?
There's tea being served outside, so you should probably kind of wind down.
We want to wind down, okay. So each of these little guys has a neural network on board that allows it to predict the future, and it helps to improve performance. I won't go into details except to mention that Alexander Gloyd-Förster, he is the head of my robot lab, and he was responsible for that 10 years ago when he was the leader of the team that won the RoboCup World Championship for the FU Berlin. Let me finally say something about the third slide again, where you saw this recurrent network, which sees, where I talked about video streaming into the recurrent network and steering a car. So this is what we have here. So we have a recurrent network which has 1 million weights and which has 60 by 60 input units, because what it sees from the video game is raw vision like this here. So a stream of these frames is running into the neural network, a few frames per second. And it's supposed to steer the car, but there's no teacher who tells the system what to do at which point in time. So it doesn't know what is a good steering movement. It doesn't know when to brake, when to accelerate. It doesn't even know that there's a racetrack and all these things. It's completely unstructured. And the only objective it has is to get a reward, which is essentially defined as maximize the time until crash. And the beginning is crash, 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 but then less of a crash, not so long, and so on. It gets better and better over time. Now it has 1 million weights, which means we have to learn a program that has 1 million components. And some of you may know that one can try to evolve recurrent networks, but and to optimize certain fitness functions or objective functions like this one. But it's difficult when there are more than a few hundred weights or more than a few thousand. We have methods that can deal with a few thousand weights, with program search in a space where the programs have really 1,000 components. But we have nothing that directly can search in a space with millions of components, with programs that have millions of components. And then what we really do here is we do compressed network search. Instead of searching among these huge programs of recurrent networks, which have many weights, we search in a much smaller space of programs that compute weight matrices. So we have this separate space of programs that compute the large programs, and we test the large program that was computed, run it in the video game, see whether it was better than the best so far. If it was better than the best so far, we keep it and build on it, and otherwise we discard it. What kind of programming language should we use to encode these big weight matrices and to search for programs in the small space that compute the large programs? In 1994, 20 years ago, I had an assembler-like programming language, an universal programming language to do this. But today we are using more practical languages based on Fourier coefficients. Imagine you have, imagine the weight matrix is an image, and then use an image compression algorithm to compress it. For example, use wavelet compression, Fourier compression. What we really do is discrete cosine transform compression. And the first authors here are Faustino Gomez and Jan Kutnik, and also involved Giuseppe Cucù in work like this. So here we search in DCT space, as opposed to the space of these huge weight matrices, and this really helps us to find strategies, policies without a teacher, without backpropagation, which doesn't work here because backpropagation works only in supervised settings where there's a teacher who knows what to do at which point in time. But here the system doesn't have anybody who tells it what to do at which time. So it has to explore the world, it has to figure out by itself what to do, and it really learns to drive the car. And the compression here is 1 to 5,000. So the big programs that drive the car can be compressed down to 200 DCT coefficients, and they contain all the stuff that the system has to do, including the vision. It has to learn vision from scratch. It has to learn certain types of memory from scratch, and how to translate these memories into steering actions at certain points in time.
How many crashes do you use in order to steer well?
I think it's a couple of thousand. It takes a couple of hours, so 4,000, 5,000, something like this. Yeah. And so, of course, you start small, and then if you don't find a small program with 10 DCT coefficients and 20, 40, 80, and so on, until you find one that is good enough. Always with a strong bias towards the simple things, the compressible things, Occam's razor in policy space. Yes. So, better use these methods not for nuclear power plants, but for toys. There will be a big market for self-learning toys, which control little artificial toy animals with fur and everything. And you say, come here, and it comes here, or it doesn't, and it doesn't matter, you know. So, yes. Yes. Do I still have 5 minutes for the formal theory of fun and creativity, or should I stop right now?
So that's cool.
Then we stop right now.
And then maybe if you're available for a little while, people can ask questions.
All right. I wish to thank the organizers for doing a great job. And there you go.
Thank you for